Okay, so hello and welcome back. So the next thing that we have here is example number 14, which is find the number of different 8-letter arrangements that can be made from the letters of the word dollar, so that all vowels occur together and all vowels do not occur together. So now let me write down the question, and then we will take care of other parts of the question. So it says that find the number of different find the number of different 8-letter arrangements that can be made from the letters of the word daughter, D-A-U-G-H-T-E-R, so that, or in such a way that all vowels occur together. Number one, all vowels occur together, and number two, all vowels do not occur together. All vowels do not occur together. Okay, so now in order to solve this problem, so first of all, to understand the problem, you want to find the number of different 8-letter arrangements that can be made from the letters of the word dollar. So the word dollar, D-A-U-G-H-T-E-R has 1, 2, 3, 4, 5, 6, 7, 8 letters. You have 8 letters here, and you want to know how many 8-letter words you can make with these 8 letters. And you can see that here basically D has not been repeated, A has not been repeated, U has not been repeated, G and H have not been repeated, T and E and R have not been repeated. So we have no problem with basically the problem that whether the objects are distinct or not. The objects are already distinct. So I can say that the objects are distinct. The objects are distinct, right? So now, since the objects are distinct, to find all the permutations of these letters, basically making 8-letter words from these 8 letters, I could simply use, for example, n permutation r, which is equal to basically n factorial over n minus r factorial. And of course, over here my n would be the number of these objects, which is equal to 8. And my r is basically the number of the letters of the words that I want to make, which is basically 8, because I want to make 8-letter words there. So by n is equal to 8, my r is equal to 8. So, and I can put these two values in this formula and calculate, for example, 8 permutation 8 and well, that way I would get all the basically permutations of this word over here. Now the problem is that that's not what I want to calculate. What I want to calculate is that you want to basically find the number of the different 8-letter arrangements that can be made from the letters of the word daughter, the same situation, but in such a way that all vowels occur together. So all vowels occur together means that basically the vowels have basically stick together. Over here you have as vowels we have A, we have U, and we have E, right? We have A, U, and E. So you want to basically count only the permutations of the arrangements in which A, U, and E basically are occurring together, meaning that, for example, it's either basically A, U, and E in the word happens either this way, or for example happens this way, or happens, for example, this way, or happens, for example, this way, and so on and so forth. All the different permutations of these 3 letters here, which is basically only 6, I suppose. So so what that means is that you want basically these 3 letters to occur in the word this way and not this way, for example, meaning that, for example, the A, E, and U must occur together, meaning that, for example, I don't want some H, for example, to be somewhere between A and E, or I don't want some R, for example, to occur over here. I don't want this to happen, nor do I want this to happen. I want these 3 to actually remain together, stick together. And of course it's important that I want to calculate the permutation of basically all such arrangements, and of course taking into consideration basically all the different permutations of these 3 letters as well, meaning that, for example, suppose that you can have A, E, and U, for example. Some possible result would be A, E, and U, and then the rest of the letters, for example, D, and then D, for example, G, H, T, and R. So you get 1, 2, 3, 4, 5, 6, 7, 8 letters here. And now these are sticking together. So you want to basically use this, you want to basically have this configuration. And also I want the permutation of these 3 letters as well, meaning that, for example, this same word, I can write it as, for example, U. I can write it as UEA, for example, then DGH, for example, TR, or I can write this the same word as, for example, EAU, for example, and then DGHTR, or I can have, for example, UEA, or EAU, or, for example, UE, for example, and then DGHTR, and so on and so forth. So you want to take into consideration also the permutations of these 3 letters as well. So now, in order to do that, what you want to do is now, since I want to stick these together, there is one way to do it. And the way that you can do that is that basically you have to suppose that, for example, you have the word, suppose that such a word exists. So, for example, ABES, for example. Suppose that this word is just some word in the English language. Now, when I want to calculate all the different arrangements of these letters, that would be basically 4 permutation 4, which is equal to basically 4 factorial over 4 minus 4 factorial, which is equal to 4 factorial, right? So that way I can calculate all the different permutations of these 4 letters, or the number of permutations of these 4 letters. Now, what I want to do here, is that when I calculate the permutation of these letters, I take this A as one object. I take this B as another object. I take this E as, again, another object. And I take this S as another object. So these are taken as 4 different objects, and for the exact same reason, I have written a 4 over here. And then, since I want to basically, out of these 4 objects, I want to make, again, 4-letter words, then I use another 4 over here, and that becomes 4 permutation 4, right? And so, if I want to calculate the permutation, all the basically number of permutations of these letters sticking together in the word daughter, what I can do is that I can basically put A, U, and E together, as basically group them together, and then treat that as just one object, just one simple object. And so what that means is that then what I can do is that basically then if I have the same word DAUGHTER, if I have this word over here, if I take D, A, and U as, if I take AU and E, as one single object, then how many other objects will I found in this word? So I said that A, U, and E are all one object. Then you have basically this object over here. This is another object. This is another object, another object, another object, and another object. So you have 1, 2, 3, 4, 5, and all of these are basically one single object. All of these are one single object. So you have 5 plus 1 is equal to 6 objects. You have 6 objects. And using these 6 objects, then you want to calculate basically, or using these 6 letters, so to say, you want to create 6-letter words. You want to create 6-letter words, and so that basically means that you're calculating 6 permutation 6, which is equal to 6 factorial. So from 8 factorial, if I had calculated this, that would have given me 8 factorial. So from 8 factorial, we got to 6 factorial. And that means that this number is, this number, if you divide this number by 56, you will get this number, of course. Now, this is the number of permutations of all such arrangements where A, U, and E are sticking together. But now the problem is that now A, U, and E, I have treated that as just one group. But the problem is that now A, U, and E is actually not a group. It is a group consisting of 3 separate letters. So those separate letters could have permutations as well. You could put A first, you could put E first, you could put U first, and then you could switch the next 2. Again, you could switch the first one and the third one, and so on and so forth. So you want to calculate the permutation of those 3 letters as well. So then the permutation of those letters would give you basically, that would be 3 permutation 3, which is equal to 3 factorial. So the answer would be 6 factorial plus 3 factorial. That would be 3 factorial plus 6 factorial. So the required number would be 3 factorial plus 6 factorial, which is equal to 3 factorial times. Okay, so now 3 factorial plus 6 factorial. So I suppose, let me see. No, of course, now the problem is that of course, this is wrong. You shouldn't add, right? So what I did, the mistake that I just made was that I wrote 3 factorial plus 6 factorial, right? Which is absolutely wrong. It's a very bad mistake to make. You shouldn't make that sort of mistake. So what I'm saying here is that, for example, suppose that you have the word as a basically one typical, for example, permutation of the word, these 3 vowels sticking together. Suppose that one typical, basically, or one example of those permutations is, for example, AUE, right? Is AUE, and then the rest of the letters, for example, DGHTER, for example. DGHTER. Now you have 1, 2, 3, 4, 5, 6. Of course, there is no E anymore, only R. So you have basically 1, 2, 3, 4, 5, 6, 7, 8 letters here. You have 8 letters here. And moreover, you have basically these 3 we have grouped them together, they're sticking together. So one such problem is that. Now, we calculated the permutation of all such basically permutations, basically keeping this just as a group of just as one object, and we calculated that permutation. That was basically 6 factorial, right? Now, so you have 6 factorial permutations there. Now, relative to each of those permutations, you need to see and you need to find out how many permutations you have basically related to these 3 letters if you don't treat them as a group of letters, and then multiply them by this answer. So let me show you what I mean by that. So for example, if I have the word, for example, TAR, So if I have the word TAR, I have 3 letters over here. If I want to calculate all the permutations of these letters, would be, for example, 3 permutation 3, which is equal to 3 factorial, which is equal to 6. That means that you can just keep this in the beginning. I mean, you can keep this and write it as TAR. You can write it as TRA. You can write it as, then use, basically bring this to the beginning and then write ATR, write, for example, ART, and then you can bring your R to the beginning. You will get R, basically, you will get RTA and basically RAT. So you have these permutations related to these 3 letters. So now when we talked about the fundamental principle of counting, when we talked about the fundamental principle of counting, we said in order to basically find out how many such permutations we can find over here, we said that, so we have these 3 letters over here. We have these 3 letters. So I have 3 letters, and out of these 3 letters, you want to make 3 letter words. And you want to calculate all the permutations related to that, right? And you want to know basically how many such words you can make. So since I know I'm making 3 letter words, so that, and then I have 3 letters over here, and if I assume that repetition is not allowed, so what I do is that I say over here, basically there are 3 ways of filling this placeholder. Now, since repetition is not allowed, and since I have already used one of the letters over here, so then I have 2 letters left, and so there are 2 ways of filling this placeholder with those 2 letters. And then basically, again, since I have already used 2 of those letters in these 2 placeholders, I have only 1 letter left, so there is only one way of filling this placeholder. And now in the fundamental principle of counting, what we do is that I say that the total ways of basically arranging or rearranging the letters would therefore be 3 times 2 times 1, which is equal to 6, which is basically the number of words that I got over here. These are actually 6 words. So why do I multiply here? I multiply here because as you can see, relative to basically, if you think about, for example, this part of this part of this operation, relative to each of these, I have 2 choices. Relative to each of these choices, I have basically 1 choice here. And let me show you what I mean by that. So the same word TAR, for example. The same word. So the same word TAR. So let's actually list all of the permutations. Let's list all of the permutations related to this word. So what I can do is that basically we have and out of this word I want to make basically 3 letter words. So I have basically the first placeholder, and this first placeholder can be filled in 3 different ways because I have 3 letters here. So I can fill it with a T, I can fill it with an A, I can fill it with an R, right? Now, the second placeholder here can be filled in 2 different ways because I have already used one of these over here. One of these I have used over here in different cases. So if I use T, then T is taken. If I use A is taken. If I use R is taken. So anyway, one of them is taken. So I have 2 ways of filling the second, basically the second placeholder. Meaning that relative to this choice, I have 2 choices left to me, which is A and R. Relative to this choice, there are 2 choices left to me, which would be T and R. And relative to this choice, there are 2 choices left to me, which is basically T and A. So that means that relative to each of these choices, there are basically 2 choices available to you. As you can see, relative to each of these choices, there are 2 choices available to you. So now in total you have 3 choices over here. And relative to each of those choices, there are 2 choices available to you. That means that in total you have 3 times 2 choices. Right? And then again, basically, if you just keep going, you can, relative to each of these, you would get 1 choice, right? Relative to each of these choices, you would get only 1 choice. So that would be, for example, an AR, so TRA, for example, and so on and so forth. And so you would get 1 choice over here, and that means that then in total you have 3 times 2 times 1 choices. Or you could say 3 times 2 times 1 arrangements. Right? So that's basically why I multiply here. Now coming back over here, I have here we established that relative to each of these, suppose that, for example, I have this AU and E, I put them together, so AU and E, I put them together, and then the rest of the letters, suppose that I get basically A, U and E, and then the rest of the letters are D, G, H, T, R. D, G, H, T, R. And I got 1, 2, 3, 4, 5, 6, 7, 8 letters here. Now suppose that I group these together and treat this as just as one object. So you have basically 3 plus 5 is equal to 8, so that's 5 plus 1. So that means that then and we calculated all of the permutations related to such words, meaning that treating these 3 vowels as just one object, and then we calculated, and then rearranging these 5 letters in all the possible ways, and when we calculated, and what we found out that was that basically the permutation related to all such permutations, the number of permutations of all such words would be 6 factorial. Now, what we found out again was that basically the permutations related to these 3 words would be 3 factorial. So that would be, because you have 3 letters over here, if I don't treat them as different letters, you have 3 letters over here, and then you want to just simply rearrange those letters in as many ways as possible. So that would simply be 3 factorial. So that means that relative to each of those 6 factorial choices, as we saw up there, relative to each of those 6 factorial choices, you have 3 factorial choices related to each of these, related to the rearrangement of these 3 letters. So that means that I can write this as 6 factorial times 3 factorial, which is equal to, well, I don't know, you could say 2 times 3 times 4 times 5 times 6 times 2 times 3, which is equal to, this is a 6, this is a 6, this is a 6, and this is a 20, so that's 6 raised to the power 4. That's 6 raised to the power 4 times 20, which is equal to 36 times 36, which is equal to 36, 3, 18, 21, 0. 3 into 6 is equal to 18, 1, 9, 10, and 6, 9, 2, 1. And then multiply this by a 2, and you have a 0 as well. So you would get 12, 1, 18, 19, 1, 4, 5, and 2, and then you get basically a 0 over here as well, and that gives you basically 25,920. Oh, okay. But we have made a mistake here. See, we calculated basically so the total number of permutations here there is a little correction that we need to make here. Okay. Well, actually, I made a very minor mistake here. This is actually 6 raised to the power 3. This is 6 raised to the power 3 times 20, which is equal to basically 36 times 6, which is equal to, that's 180, and that's basically 36, which is equal to 6, 11, 216. 216 times 2 is equal to 12, 1, 2, 3, and 4, and that's 4,000. That's 4,320. Okay, so now to basically to address the second part of this question, what we need to do is that basically the question is that you want to find basically the number of different 8-letter arrangements that can be made from the letters of the word dollar in such a way that all the vowels do not basically occur together. When all the vowels do not occur together, that means that basically what you need to do is that basically you take all the different permutations of these words, or of these basically, well, of these words, and then you can take out all the permutations in which the vowels are always together, and then that means that then you will get basically the permutations when the vowels are never together. So all the possible permutations of these. So then what you need to do is basically you need to, for example, take A as, for example, the permutations the permutations when basically when or you could say all the possible permutations of the 8 letters. You have 1, 2, 3, 4, 5, 6, 7, 8 letters. So you can take this as all the permutations of the 6 letters. And then B, for example, you can calculate all the permutations. You can calculate all the permutations when the vowels occur together. And now if you write A minus B, this would be all the permutations in which the vowels are never together. Okay. Now all the permutations of the not of the 6 letters, but we have 2, 4, 6, and 8 letters, of course. I'm sorry, I made a mistake here. So you have all the permutations of the 8 letters. So that would be basically 8 permutation 8, for example, which is equal to 8 factorial. And so that is equal to, for example, A. And B is all the permutations when the vowels occur together. So we have already calculated this to be 6 factorial times 3 factorial. B, we already calculated that as 6 factorial times 3 factorial. So you can write A minus B as basically 8 factorial minus 6 factorial times 3 factorial, which you can write this as 6 factorial times 7 times 8 times minus 6 factorial times 6, for example. 6 factorial times 6, because 3 factorial is equal to 6. And then you can take a 6 factorial out, and then that's 7 times 8 minus 6. That is 56 minus 6, which is equal to 50, which is the same thing as 6 factorial times 50. And 6 factorial times 50 is the same thing as, is the same thing as 1 times 2 times 3 times 4 times 5 times 6 times 50. So this is equal to 6, and this is equal to 6, that's 36. 36 times 20 is equal to 720. So 720 times 50. 720 times 50. 2 zeros there. 0, 1. 35, 36. So that's 36,000. That is 36,000. Okay. So that's, for example, how you would calculate this example. But you basically you do need to understand each and every part of this question the way that we did it, so that you can. Of course, we will get to other examples here, and we will understand all the other ones as well. So there is really nothing to worry about. So we have another example here, example number 15, that says that in how many ways can 4 red, 3 yellow, and 2 green discs be arranged in a row if the disks of the same color are indistinguishable. Okay, so you have 4 red, 3 yellow, and 2 green disks. So you have 4 red disks, you have 3 yellow disks, and you have 2 green disks. And then basically we know that the disks of the same color, we know that the disks of the same color are indistinguishable. That's a long word. Distinguishable. Well, you know that the German language is known for long words. For example, you have the words like in the German language you have words like, for example, Dorf, Gemeinschaftshaus. Dorfgemeinschaftshaus. That's a word in German. That means, for example, something like Dorf means village. Gemeinschaftshaus means the kind of house where everybody in the community get together. So that means, well, the house in the village where everybody in the community get together, or something like that. Now, the German language is of course known for long words, but then I'd never actually come across basically words as long as indistinguishable in the English language. So you have basically 4 red disks, you have 3 yellow disks, and you have 2 green disks. And we know that the disks of the same color are indistinguishable. What that means is that, for example, you can treat the 4 red disks as basically one object. Or you could treat the 3 yellow disks as probably as one object, and so on and so forth. But I'm trying to find an example where I can fit this into the examples that we have done before. Okay, so now how we can solve this problem is that you can think of these as, for example, you have 4 red disks and 3 yellow disks and 2 green disks and so on and so forth. So what you can think of these as, for example, the letters of a word, for example, and we have already solved that problem. For example, we had the example of the word institute, and so, for example, over here we had 2 I's, and we had basically 3 T's, and we had, I think that's it, U, and so these have been repeated, right? So that means that you can say that for example, the 3 T's, that means that you can say that the 3 T's are indistinguishable. if that's correct. Or you can say that, for example, again the same thing, the two, for example, eyes are, for example, indistinguishable, and so on and so forth. And how we solve this problem, we said that, and you saw that the problem that you could get into when these things, basically when these objects repeat themselves, meaning that we had the problem of the word, there was a word that we had over here in the beginning of this section, root. We have the word root, and in the word root, O basically appears twice. So in this word, we came across, basically we had two, relative to four different, basically relative to four different letters, you would have 4 factorial permutations. Meaning that you would have 4 permutation 4, which is equal to 4 factorial, which is the same thing as 4 factorial over 0 factorial, or you can say that 4 factorial over 4 minus 4 factorial, which is equal to 4 factorial over 0 factorial, which is equal to 4 factorial. So relative to these two, relative to these four letters, you have 4 factorial permutations. But then the problem was that we saw all of those words, like for example O1T02 and R02T01, that repeated themselves, and there were 12 of these. There were 12 such pairs that repeated themselves, because these O's are repeating themselves. And so what we had to do, we had to divide the number of the permutations related to these 4 letters, which is basically 4 factorial, and we had to divide this permutation by this number by the number of permutations of the 2 letters, which is 2 factorial, and that was basically the distinct number, the number of distinct permutations related to this word root, for example. If you do not basically treat the 2 O's as different O's, if you treat them as the same O's, then you have to divide basically your 4 factorial by 2 factorial in order to get the number of basically permutations of the distinct basically the number of distinct permutations of the word root. So that's how we solved this problem. We can use the same thing over here, meaning that we can basically go over here and, for example, say that for example I have 4 red discs over here, 3 yellow discs over here, and 2 green discs over here. And for the time being, I'm going to treat these discs as distinguishable, not indistinguishable, but as distinguishable, meaning that I can call these, for example, R1, R2, R3, and R4. I can call these, for example, Y1 and Y2 and Y3, and I can call these, for example, G1 and G2. So now I have 1, 2, 3, 4, 5, 6, 7, 8, and 9. 8 and 9 distinct objects. Of course, that's actually not the case, because over here we have said that basically the discs of the same color are not distinguishable or are indistinguishable. But here, for the sake of simplicity and because I want to find some way to solve the problem, I'm assuming that I have 9 distinct objects, treating them as, for example, R1, R2, R3, and R4. So the permutation related to these 9 different objects would be, of course, 9 permutation 9, which is equal to 9 factorial. Now, of course, since you know that since these are the number of the, and of course you have to take the permutation of these, of the objects that are indistinguishable, you have to take them out, meaning that once you have this number, you have to basically then divide by the number of permutations of the for example the 4 red discs or the 3 yellow discs or the 2 green discs and so on and so forth. So then that means that basically I can say that the total number, the required number of permutations is equal to basically the number that I got here, 9 factorial, but then I have to divide by basically, for example, the permutation of these 4 red discs, which is basically 4 factorial. The permutation of these 3 yellow discs, which is 3 factorial. The permutation of these 2 green discs, which is 2 factorial. And so if you calculate this, you will get, for example, something like you would get something like, for example, 4 factorial times 5 times 6 times 7 times 8 times 9 divided by 4 factorial times 6, for example, times 2, and then these 2 can cancel out, these 2 can cancel out, these 2 can simplify, and then you would get 35 times 36, for example, 9 times 4 is equal to 36, and this is 35, and you would have basically 5 times 6 is equal to 33, 15, 18, 0, 18, 1, and 9 and 10. So you get 0, 16, 2, and 1, 12, 60. You will get 1260. So for example, that's how you would solve that's how you would solve this problem. Again, we have another example here, which is find the number of arrangements of the letters of the word independence, and how many of these arrangements do the words start with a P, do all the vowels always occur together, do all the vowels never occur together, and do the words begin with I and end in P. So this is also a typical example that you need to understand how to solve, because, well, at least in these series of books, everything is just simply based on, I mean, you do need to understand how to do these in order to be able to do the next things and so on and so forth. So the question is, find the number of arrangements of the letters of the word independence. Find the number of arrangements of the letters of the word independence. Dependence. And you want to know in how many of these arrangements in how many of these arrangements do the words start with a P? Do the words start with a P? Or do all the vowels always occur together? Or do all the vowels always occur together? Or do the vowels never occur together? Number 3, do the vowels never occur together? Or do the words begin with I and end in P? Number 4, do the words basically begin with I, and end in P? So we want to answer these questions, right? And this is a typical question that you do need to understand how to solve, and you need to you do need to understand everything about this problem. We will do that together. Okay, so now in order to solve this problem, first of all, we want to find the number of arrangements of the letters of the word independence. So the first part is easy. So you have basically independence, independence. So in the word independence, first of all, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 12 letters. You have 12 letters. Now n basically appears 1, 2, 3 times. N appears 3 times. And D appears 1, 2 times. D appears 2 times. E appears 1, 2, 3, and 4 times. E appears 4 times. And P appears 1 time. Then you have C, which appears 1 time, and so on and so forth. So these are the only repeating letters that we have, and we have 12 letters in total. So that means that the number of permutations of this word, and you need to understand what I mean exactly when I say permutation. Permutation means all the different ways of arranging the letters of this word to get words of the same number of letters in such a way that you don't get repeating results. Okay? So let me write this down, because maybe it's actually my second time that I'm going through this chapter. Probably it's second time, and of course I mean you think that you have understood the chapter the first time. Well, you read the chapter, you even teach the chapter, and you solve all the problems, and you think that you've understood the chapter. I mean, that's a safe assumption to make. But then after I've gone through the chapter once, not reading it basically in a normal way, but actually teaching the chapter, although I've never actually published those videos anywhere. And then solving all of the problems related to that chapter. Now in the second, basically, now this is the second time that I'm doing this chapter because I needed to for the last chapter in this book. Now basically the second time that I'm teaching this chapter, now this time I'm actually understanding this chapter. Otherwise the first time I can't really say that I understood the chapter in any way. So that what I mean by that is that chances are that you think that you're understanding what I'm saying, but you're really not. So now what I mean by the total number of, for example, when I say the total number of permutations of the letters of the word, well, whatever that the word might be, that doesn't matter, the word independence, it means all the possible ways. What this means is basically all the possible ways that you can rearrange the letters of the word, so all the possible ways that you can rearrange the letters of the word to make words, or to basically to create words of the same number of letters in such a way that you don't repeat the letters, that you don't repeat the letters, and also in such a way that, and there is no of here, of course, in such a way that you get distinct, meaning not repeated words, right? So the total number of permutations of the letters of this word. Now you can think of the letters of the word as different objects that you might have, right? And so then if I said the total number of permutations of the letters of the word, you could think of that as, for example, the total number of permutations of, for example, n number of, for example, objects, distinct objects, right? Now, of course, in a word, for example, the objects might not be distinct. That's possible, but, well, we are assuming that, for example, the objects are distinct. And so when I say the total number of permutations of the letters of the words, what that means is that all the possible ways that you can rearrange the letters of the word to make words of the same number of letters. Of course, it's possible to make words of different number of letters, and, well, in that case, for example, the permutation would be called something else. For example, if you have 12 letters over here, if I'm assuming that I'm making words of the same number of letters, then you would be calculating, for example, 12 permutation 12. Otherwise, for example, if you're using these letters to make, for example, basically 9 letter words, then you would be calculating, for example, 12 permutation 9, right? That's also possible, which is not a problem. That's a part of our definition. It can be a part of our definition. So you could say that basically that all the possible ways that you can rearrange the letters of the word to make words of the same number of number of letters, or basically just to make words of different number of letters for that matter, as we discussed here, in such a way that you don't repeat the letters, and also in such a way that you get distinct words. So these two you need to also understand. So when I say in such a way that you don't repeat the letters, that means that, for example, you have for example 12 letters in here. So when you have 12 letters in here, and let's assume that we are making 12 letter words out of those 12 letters. So I have 12 letters. So I have 12 letters, and I'm creating 12 letter words. So that means that I have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 12 placeholders as the placeholders for the letters over here. Now what that means is that, for example, since I have 12 letters in here, then of course you know that the first placeholder can be filled in 12 different ways. The second placeholder can be filled in 11 different ways, not in 12, because you have already used one of the letters here. The next one can be filled in 10 different ways, 9 different ways, 8 different ways, and so on and so forth. That means that what you have used here, you're not supposed to use it again. That's the meaning and the definition of permutation. And you're already familiar with this concept. And so we say that in such a way that you don't repeat the letters, and also in such a way that you get distinct words. Now, this is also something different, meaning that sometimes you don't repeat anything, but in spite of that, you don't get distinct words. For example, in this case, you can see that, for example, N appears 3 times here. So as you saw with the case of the word root, where basically O appears 2 times in that word, that just gets you into trouble, meaning that it creates, for example, I don't know, 4 factorial, for example, permutations for you, but then you have to divide that 2 factorial you have to divide by 2 factorial to get the number of distinct permutations of the word, because these two O's are actually not distinguishable. They are not distinguishable. So they create repeated results for you. So you have to take care of those things, which is basically N, D, and E in this case. And so you have to take care of them so that you don't get repeated results, or in such a way that you get distinct words in your results. And this whole situation, I refer to it as, well, when I'm talking, since I have already talked about this here, basically in the form of a very clear definition, then when I want to talk about this concept, I just simply call it the permutations of the word, for example, independence, and then you understand what I'm talking about. And that's actually the beautiful thing about mathematics, that you can actually, it's possible using logic to define things very clearly without any ambiguity or without any misunderstandings, and then you can talk about them, use a word, and then everybody knows what you're talking about. In other areas of life, it's not possible to do that. It's actually still not possible to do that, especially when it comes to human mind and everything, all the concepts related to human mind, then it's still not possible to do that. But when you're talking in mathematics, it's very easy to talk, very simple to talk, and it's very elegant, very effective, very organized. It's the most elegant and the most beautiful system that I've ever known in my whole life. I admit to that, really. Anyway, we will end this video here, and then in the next video we will talk more about this example.